Okay, well, thanks for everyone coming back from lunch or whatever part of the world you're in, whatever meal you're eating. Um, we uh, we have an exciting part of the program, a technical part of the program coming up. Um, this is going to be session 3, the bright future of image acquisition, calibration, and artificial intelligence. And I'm told I need to introduce myself. So I'm Rick Avila. I run a small company called Accumetra, and I'll be talking a little bit about some of the things we do. But I'm a computer scientist, have been working in the field of AI since 87, I think it was. Yeah. And I've worked with a lot of people here at the meeting. Um, and I'm joined with a fellow moderator, Tony Reeves. Tony Reeves is a professor of computer science at Cornell University in Ithaca. And he is one of the original people, part of LCAP, that started the ball rolling on nodule volumetrics back many, many years ago. And he has many other innovations to his name. So thank you for joining us, Tony. In addition to that, we have 2 really exciting panels. One is on this topic of artificial intelligence and CT image reconstruction. We all know it's coming, or it's here in some cases, and there's quite a lot to discuss there. So we're going to be given a talk by Bruno. He's at GE Healthcare. He is a foremost expert in CT image reconstruction, and he has some really good thoughts about how AI can be integrated into the CT workflow, and image formation in particular. In addition to that, we have Andreu Badal. He's from the FDA, and he's a physicist. And we're very fortunate to have you as well, Andreu. Thank you for joining us. And then Brian Nett, also from GE, a medical physicist who is actually quite famous for providing YouTube videos to the world and telling us all how we should think about CT imaging and how to get the best use out of CT scanners. And then finally, we have Adam Wang. Adam is at Stanford University, also in medical physics. And I was told, well, I know that he's part of an esteemed medical physics group at Stanford. So thank you, Adam, for joining us. I'll introduce the second panel when we get to that, but I have some initial slides to go over. So why don't I just jump into my slides? Share my screen. I'm sorry. Okay, so I'm going to share my desktop and go into presentation mode. Everything good? Are we good? Okay.
Yeah, it looks good.
All right. So the first thing I think is really important to say is a huge thank you to the Prevent Cancer Foundation for really allowing us all to get together every year to really push the field forward in terms of lung cancer screening, but also COPD and cardiac diseases. And really, without this meeting, I don't think we would have made anywhere near the progress we did. So thank you so much. Yeah, let's just talk about sort of how some of the things we've learned over the years. So this is a slide from a long time ago. This was actually Mount Sinai or Cornell data, LCAP data, I think it was. This is zero change data with 0.625 millimeter slice thickness. And as the lesion size gets smaller, the air, we should have zero basically change. Each dot shows the amount of change between two scans that were pretty much the same, scanned just minutes apart. And as the size of the nodule gets smaller in diameter, you can see that the spread of the error gets bigger. And we, of course, model that. And in the KIBA small lung nodule profile, we came up with estimates if everything goes bad, you have like you've got, let's say, a big field of view, and you've got a scanner at the lowest resolution that that will allow. You'll have a minimum change that you see on the right that we think bounds the error. And that serves the purpose of giving us a way to guide sites as to how much error to expect, even under some of the worst conditions, like a nodule out in the periphery, for example. So we, before this, we kind of used a constant for how much error there was in a change calculation, and now we started to really get into what the differences are with different size nodules. We also saw in 2010, and we were the first to report that you could see what really large amounts of change. Again, in a zero change situation, you put a phantom on the chest of a patient in a clinical trial like you see here, and you could see a 44% change or plus or minus 44% change in a 1.6 centimeter sphere when it shouldn't have changed at all. And most of that was coming from the Z direction. So we were the first to report that. We covered a lot of other ground. I'm not going to have time. Just one of the fun things that we did was we distributed tape around the world, Scotch tape, and we had people scan it. And we said, well, if you scan Scotch tape and you submit it to us on the cloud, we'll predict for you the performance of your CT scanner at different, basically for different size lung nodules. And we had 27 international sites do that. And we learned a great deal about how to essentially predict what a scanner is going to do. There's many other things here, and we recognized that I've been using this slide for years, that AI-based measurement methods and even changes in reconstruction, which might use AI, could really change what we see in the scans and how we measure them. We also learned that not all CT slices are the same. A slice is not always the classic appearance of a slice of bread, like you see on the left. It can flare out. This is not exactly to scale in X because that would take up a much larger and thinner slice. But you get the point. We basically have some scanners making slices that look significantly different and have significantly different resolution in different dimensions than other scanners. And one of the biggest accomplishments was we created a very low cost phantom that can be automatically analyzed on the cloud, and a report can be given back in a few minutes. And we created the first conformance certification process with KIBA and RSNA, and we created that conformance certification mark that you see on the left. Unfortunately, now KIBA is kind of winding down, but this lives on and is being used around the world quite a bit these days. In fact, we have over 125 global CT scanners right now being monitored and optimized with a cloud analysis occurring in the US and Europe. And again, many thanks to the Prevent Cancer Foundation. They provided the initial funding for both the CTLX-1 and the CTLX-2, which was distributed in Poland, and is now, again, supporting entire countries around the world. This is now becoming essentially a global standard for CT imaging of lung nodules. This is the CTLX-2, which is the widest CT phantom that I'm aware of in the world. It's also very low cost because it uses water bags to add mass to the phantom. It's 3D printed, and we can put 3D printed objects inside of it. So it's really improved our ability to understand the performance of CT scanners, even when large patients are within the scanner. And then we also developed the open source lesion sizing toolkit, and we've been maintaining that all these years. And we created COVID-19 CT lung imaging guidance when that was a major issue, and we've been providing guidance to the world now for several years. And also, we've been making phantoms with large numbers of ellipsoids in them, and looking at how commercial software performs at different size objects. And you can see some problems on the right, which I don't have time to get into, but we've been doing all this and cataloging how scanners and how software are performing. And then finally, I'll give a presentation later where we now have some very highly promising AI methods that could greatly improve our ability to image and also measure small objects like lung nodules and airways and other things. So if you look at the things that we've managed to accomplish, and I mean we, because very large numbers of international groups and people have been involved in this over 20 years. It's really amazing. It really is. And I want to thank everybody who's been involved. We've definitely set up something that is actually growing now in use and adoption throughout the world. So with that as the backdrop, we have two important panels today, as I mentioned before. The first one is going to be on integration of artificial intelligence in CT image reconstruction, which I introduced the panelists before. And the second one, I'll cover this exciting new opportunity that I just showed you a peek of. So what I'd like to do now is, with that as the background, hand it over to Bruno de Man to give his presentation on AI and CT image reconstruction. Bruno?
Great. Thank you, Rick. Let me try to share my screen. Okay. Yeah, thank you for the invitation to participate in this great workshop, and thank you for all the panelists for joining this interesting discussion. So I'll give an overview of AI in CT. We've been supported by several NIH grants and working with several academic and clinical partners on some of the work that I will show. So if you think about AI in CT, or actually reconstruction or tomographic reconstruction in general, you can distinguish three general phases. In the early stages, everybody was using mathematical inversion. So you can think of a scan as represented by a mathematical formula, and you can then come up with a mathematical inversion formula, and your reconstruction just follows that mathematics. Now, in the real world, everything deviates from the ideal mathematics, and you have a lot of physics effects, noise and beam hardening and spectral effects and scatter, etc., which makes this very suboptimal. And so maybe about 10 years ago, a lot of groups were switching to iterative reconstruction, model-based iterative reconstruction. So here we can build a very complex model of your scanner, a computer model, and then invert that model iteratively or numerically. So that was the switch to iterative reconstruction. That was very powerful in terms of reducing image noise, reducing artifacts. But now, a couple of years ago, or maybe almost 7-8 years ago, we started looking into data-driven reconstruction or deep image reconstruction. So we don't rely on the mathematics anymore. We don't rely on the numerical inversion anymore. We rely on data. So we learn from a large amount of data what the right outcome is for AI. And so now the real secret sauce is in the data, really. How can you generate good training data that represents what you want to do? Then just take your time to train the neural network and show that it can do it reproducibly. So let's look at a CT scanner. CT scanner is essentially a big 1-ton gantry. It rotates multiple times per second. Essentially, 140,000 volt goes in, a gigabit per second worth of data comes out. And so that's even true for an older scanner, but as we are developing modern photon counting CT scanners, the order of magnitude more data will even be produced. So we all know that data is important for AI, so it seems like CT is a great location or place to apply AI. However, what should data look like? What are the requirements for good AI training data? So first, it needs to be clinically realistic. You cannot train your algorithms based on water cylinders and then apply them to real patient data. On the other hand, you need very good ground truths. So you need pairs of data, input data and corresponding label data that's very well controlled. Those two requirements are a little bit contradictory. You can usually have great clinical data sets, but then you don't have ground truths, or vice versa. You can have very controlled data sets, but then they're not clinically realistic. So what we've focused on a lot over the last many years is virtual CT data generation. So we've developed virtual CT scanners, so basically advanced physics models of real scanners. And what we do is we use clinical data sets that are high quality, use them as the input for the simulations, but we add artificial features to that, as shown some examples on the bottom here. So we can, for example, when we want to look at calcium deblooming, we add virtual calcifications on top of a real clinical data set and pass both of them through the CT physics process, acquire raw data, reconstruct them, and the result is we get a CT data set with calcium blooming. But we also know the ground truth of the calcifications since we defined it ourselves, so we can have a good training pair. Second example here is virtual metastasis. So we superimpose virtual liver metastasis on top of a clinical data set. Third example is metal artifacts. We take a pristine clinical image, add metal artifacts, metal objects on top of that, and simulate all the real physics to generate very realistic metal artifacts. So we've used this framework in several opportunities, and it's proven very, very handy. And by the way, this simulation framework is available publicly through github.com/exist if anybody's interested. So let's have a look throughout the CT imaging chain. What are some of the opportunities for AI? Starting from the setup of the scan, we can use AI to optimize the actual scan protocol. We can use AI in the early stages where we look at sinogram data and process the sinogram data. We can use it to do the actual reconstruction, so to convert the sensor data to images. We can use it to improve the images, enhance the images, or we can use it to analyze the images and extract diagnostic information from it that goes into reports. So I'll walk through each of these examples in the next couple of slides as some proof of concepts. So the first example is the control of the actual scan protocol. So we're actually still, this is a project that's underway, but we're developing an autonomous cardiac CT scanner. So we are using a pulsed X-ray source that's pulsing once per rotation or twice per rotation. So very, very sparse pulsed X-rays. And then we're analyzing the projection data in real time with AI. We're extracting two pieces of information. One is the cardiac phase, and one is the bolus enhancement in the heart from those very sparse projections. Once the AI determines that both conditions are satisfied, the bolus is in the heart, and we're at a quiescent phase of the cardiac cycle, we start the actual scan, and the X-ray tube goes on continuously. So this really allows to turn a very complex exam that's very hard to time into a fully autonomous exam that's easy and robust using AI. So let's then look at the whole image generation chain and think, where can AI help at the different stages of the image generation? So looking at the raw data sensor domain, there it's all about physics. Can we use AI to model or correct for some of the imaging physics? Then you have the imaging geometry. So to convert sensor data to images, you have some geometrical mapping. AI could learn that mapping in case the mapping is unknown or the mapping may be imperfectly modeled by our assumed geometries. Then you have the actual inversion process. How do you take a bunch of data and decide on what the image solution is given all these data? So that's like the imaging mathematics. And finally, you have image domain prior information, like AI can learn what typical images, good images should look like in terms of what's noise and what's real. So that's the imaging prior. These are all opportunities for AI to learn. So first example here in sinogram space is, can we actually bypass reconstruction and just learn or do analysis directly in sinograms? And this was a brief proof of concept feasibility study where we showed that, yes, AI can detect blood vessels directly from sinograms without ever doing reconstruction. And it can characterize their cross-section directly from sinograms. So future work will be, can this actually help us? Are there opportunities to do things that we couldn't do through reconstruction and then analyzing images? Another example in sinogram domain is metal artifact reduction. So one approach to metal artifact reduction is to interpolate missing data that's shadowed by the metal objects. And so traditionally, this has been done by handcrafted approaches for decades, and those approaches have become more and more sophisticated. Like here you see image without metal, image with metal corrected with the traditional analytical approach, normalized MAR, NMAR. You see still some residual artifacts there. So we developed a diffusion probabilistic model for sinogram completion and shown here that the images already look much better, at least in this example, compared to the handcrafted approach that has evolved over decades. So we think there's a big promise there. Now let's go to the actual reconstruction. So that's probably the most challenging application of AI. The reason is we're going from one domain to another domain, and the domain transform is a very high dimensional transform. So even in 2 dimensions, the sinogram is on the order of 1 million numbers. Images are on the order of 1 million numbers, and the system matrix is not entirely sparse. So you have a system matrix on the order of 200 billion numbers. So doing this transform with a brute force neural network becomes very intangible. So we've come up with a more heuristic AI approach, trying to build on how humans would solve this problem and teach some of that to the AI. So the basic idea is that if a human looks at an object from a couple of slightly different angles, you get some depth information, limited depth information. As you look from even wider range of angles, you get more depth information. And if you turn all the way around the object, you get complete depth information. So let's structure the problem that way and let the AI solve it that way. So we take a number of projections that are neighboring projections together, let the AI estimate some line integrals from that, partial line integrals. So it starts with full line integrals, and it's trying to estimate some partial line integrals, combine even more views together, and get even smaller line integrals. So as you combine more and more views, the AI learns to get more and more depth information. And eventually you combine all the projection data, and the AI gets complete depth information and does reconstruction. So we implemented this approach and demonstrated that without knowing anything about the geometry, the mathematics, the AI could learn a full-sized 2D tomographic reconstruction that's equal or better than filtered back projection. So this is not yet extended to 3D, but this at least has some very favorable properties. So the reconstruction complexity is on the order of n log n, where otherwise it would be order n squared. And so we think this is one of the only ways we could generalize this to 3D to do AI, pure AI reconstruction. So then we get closer to the image domain, motion compensation. So you could still call it part of the reconstruction. In this example, we used 3 reconstructions that are slightly offset in time. And then we use an AI network to estimate the motion vectors from 3 slightly offset reconstructions. Once we know the motion vectors, we can do a new reconstruction that incorporates the motion vectors and do a motion corrected reconstruction. So looking at AI to further refine the traditional analytical methods. So then one of the most popular approaches or applications of AI in CT is denoising. And here's some of our work in collaboration with University of Madison and RPI. The first image shows uncorrected traditional filter back projection. Second image shows an iterative type of approach, and the third image shows an AI type of approach. So you can see that AI has some remarkable capability of suppressing image noise while still preserving some of the anatomical details. You can also look at the noise power spectrum. AI has a better ability to preserve the desired noise power spectrum that improves detectability compared to some iterative reconstruction techniques. Another example is deep learning super resolution. So here we're trying to use AI to generate higher resolution images than would be normally possible with the existing hardware, instead of using very expensive hardware improvements to get to that result. And so you can see in this is a cardiac exam, but you can see some of the lung aspects there too, where you get much better spatial resolution and reduced noise or aliasing artifacts when you do the deep learning super resolution. Last example is an image analysis example that we have been developing in our team. So trying to extract some functional information from a cardiac CT exam. So when you have a stenosis, we also want to know what's the pressure drop across that stenosis, or what's the hemodynamic significance of that stenosis. So in order to do that, you first need to segment the coronary arteries, and then you need to compute pressure distribution across the coronary tree. And so all of this is done with AI here. So we use AI to segment the vessels, which was, again, trained with some of the simulation framework that I showed earlier. And then we use AI to estimate the pressure distribution, which was trained with full-blown CFD computations, which take a long time, but AI can do essentially the same thing much faster. So this leads to a prototype that's very fast and can estimate CFR with minimal human intervention. So in summary, I showed a number of examples of AI throughout the CT imaging chain. If you're thinking about the future, here are some of my predictions. So one is generalizability. Simulations, we've shown that it's offering a very powerful way to generate good training data sets, but we still, in some cases, need to address the domain shift from our training data sets to the actual real clinical cases. So that's a challenging a challenge we foresee no matter what your training data sets are, the generalizability. Second big challenge is the stability or the risk for hallucinations. So especially with generative AI, it is very powerful, but sometimes it may risk creating hallucinations, and that's a problem that still needs a lot of attention. So then I think eventually the combination of physics and AI will offer the best of both worlds. Like the example I showed about reconstruction using the hierarchical approach, that's really incorporating some human intelligence with AI to make it possible, where otherwise it would just be intangible or impossible. And lastly, we're really leveraging a lot of the computer vision industry. We've gone from CNNs to UNets to GANs to transformers, diffusion networks, and it's exciting to see what will come next. So finally, I want to show what the relevance of all this is to specifically quantification of small lung nodules, because a lot of this work was not done in the context of lung nodules. So first, one obvious translation will be training with CT simulations of clinical images and virtual nodules. That seems like a natural extension of this work. Then personalized protocol optimization. So we probably want to, depending on the patient, decide on what's the best spatial resolution, probably relatively high resolution in most cases. and how can we minimize the noise and minimize the dose, so optimize the protocol to the specific patient. Then we can optimize the scan timing using based on minimal respiratory motion, and then also correct for any residual respiratory motion. Super resolution and denoising are directly translatable to this application. Of course, AI for detection and quantification, that's a widely investigated application. And then direct sinogram analysis, it could be that maybe analyzing nodules directly in sinogram could potentially have some benefits in some cases. So this was a high-level overview, and looking forward to further discussion.
All right. Thank you, Bruno. What we'll do is, just to stay on time, is to try to have the other panelists give their thoughts. Andreu, would you be okay giving your presentation now? And we're going to try and keep it short, right?
Hi. Thank you, Ricardo, and thank you for the invitation. So I'm Andreu Badal from the FDA. I do research, but also work on the regulatory evaluation of this kind of CT reconstruction software. This is definitely a very exciting technology. I think we all recognize the potential. I would like to say regarding the FDA regulation, these kind of devices are regulated what we call a 510K process. So they have to demonstrate that it's substantially equivalent to the previous devices. So most of these have been demonstrated to be equivalent to the previous CT reconstruction algorithms. And I think we all agree that they are at least equivalent. That's probably not the best that we can do. We want them to be better. And some of them definitely are better. And I think there is a still need for finding metrics and phantoms and ways to characterize how much better are these AI and how to prevent these hallucinations or other problems that are not common in previous kind of algorithms. There are applications like this denoising, super resolution that are very interesting. These are kind of algorithms that we could do also without AI, but we know AI seems to work better. But still, there are not very clear metrics unless you have like perfect ground truth. It's difficult to get a patient image, increase the resolution, and say that geometry is really better representation of the anatomy. You need ground truth for that. So that's kind of a research challenge, really, that we are trying to figure out. Many of the phantoms that Ricardo was showing before were very useful in the standard CT reconstructions, but I'm sure he's working on how to adapt them to the AI world, because any phantom that is not completely realistic, it's out of distribution for an AI algorithm. And there is always a question how much it represents the exact performance in the patients. And also there's always a question, are these AI algorithms trained using phantom images or only patient images? There are some cases where you would want to include phantoms, but then the evaluation may be kind of corrupted. And that's the other thing of generalizability, that definitely it's something that at the FDA we always request testing in different scanners and different variety of patients, but there is always with AI the problem of possible bias in some subpopulations. And finally, to finalize, another interesting aspect is that this AI reconstruction can be applied in different ways. It can be included inside the reconstruction itself, so with access to the sinogram, the raw data, or it can be used as a post-processing after reconstruction. And both methods work, but it's probably one method is better than the other. From physics principles, it looks like if the network has access to the raw data, it has a better chance to perform. And when you compare to the other point, when comparing to iterative reconstruction, we have to consider also the iterative reconstruction. It's really good. and it has regularization parameters inside. So it's another important concept that comparing the AI to iterative cannot be done with just one image. You need to find the regularization, like the best image quality, let's say, in both, because iterative reconstruction algorithms are really good. They have a lot of physics inside, a lot of things that mathematics dictate it's optimal. So it's still a very good technology, and hopefully AI will only make it better. That's it. Thank you.
Thank you very much. Brian, what are your thoughts?
Sure. I'm just going to share a slide quick. Hopefully this works. All right. Yeah, so I'm on the GE team also with Bruno, and I'm focusing on the application of these networks, especially for denoising. So just talking about those first, like what Bruno talked about, we went from filtered back projection to iterative reconstruction, more advanced iterative reconstruction methods, including model-based methods, and then deep learning methods, kind of, you know, over time, just adding more and more complexity to the model-based methods.
Hey, Brian.
And now these deep learning, yes.
Real quick, can you go up to the top left of your screen and swap your displays? We are seeing your presenter view, not the full screen slides. Display settings. So go to display settings and swap presenter view and slideshow.
Okay, how about that?
We are still, yep, there we go. Thank you.
Okay, yep, I appreciate it. Yeah, so again, just at a high level, everyone, all the vendors have been working in this space of improving the image quality, especially denoising via the iterative reconstruction algorithms. And then a major complaint in the area is actually the texture in the images. And that's the major thing that we've been able to improve via these neural networks to train to reduce the noise in the images. So multiple of the vendors have solutions here. And there's also solutions that can run on DICOM images as well that are third-party solutions. And then I just have a couple examples of things from the literature as far as quantitative measurements. Obviously, like you just heard, the vendors work with the FDA. Part of our FDA submission was involving taking measurements on a lung phantom like this. But in this paper, the authors looked at different doses, different KVPs. This is kind of a moderate dose and then an even more reduced dose case. And they looked at also some different sizes of nodules. So here's the sizes of the nodules that they had. And then they evaluated from left to right. This is the ACER, the iterative reconstruction. Then here's the true fidelity. And then this is the ClariPy. So this is a third-party solution. And then this is even lower dose, looking at ground glass, whereas these are solid nodules. And then you can see this is a summary table showing that for all the measurements on these phantoms, they were seeing essentially less than 10% error in these size measurements, and that in general, the neural networks performed better than the iterative reconstruction. There's also been some work in the area of starting with a higher dose exam and comparing it. That's what the reference is here, and then comparing it with the ultra low dose exam and using quantitative metrics which isolate the regions within the lung, then apply the quantitative metrics inside of those regions. And then this also shows that there's improvement in this area when using the deep learning image reconstruction. And we've also worked on evolving this from first we did it with single energy on one scanner. And then like you heard, we're actually doing this 510K process for every scanner essentially. So we've done 4 different additional scanner geometries that are slightly different with the FDA. And then as well, supporting our dual energy technology. So we have a separate set of training that we've done there as well. And this is just an area that we feel is really enabling us to kind of push the boundary for some dose reduction here, but the main thing is improving the texture in the images. And I'm looking forward to the conversation. Thanks.
Thank you so much, Brian. Next, we have Adam Wang. Adam.
Hi, everyone. Thanks for having me on as a panelist. Yeah, just to echo some of the things that were said and maybe offer a couple of thoughts. One, I really also see that one of the challenges is in getting realistic data but also where you have ground truth for training purposes. Bruno mentioned, the nice work that they're doing with the realistic simulations. So that's certainly one way of doing it. I'll just offer a couple more ideas there. One is a class of what you might call self-supervised learning, where the data also somehow offers you the reference as well. And without getting into too much details, this has been pretty effective in applications like denoising, where noise is random. And so if you're able to somehow either get a separate scan or independent noise, that you can at least look past the random elements. And so that's fairly effective for denoising. And then others are looking at maybe physical phantoms. So again, rather than the digital phantoms, creating realistic physical phantoms. And so maybe 3D printing or other ways of printing realistic patient anatomy and also pathology as ways of then having, again, a ground truth, as well as being able to collect realistic data. The other comment that I'll offer is that I'm a big fan of physics-guided AI as someone who does a lot of CT physics research. I think this is probably, and Bruno touched on this as well, but this is probably the most powerful combination where the physics can offer a lot of very valuable information. So rather than just treating everything as a black box and trying to learn a lot of things that we do know about CT, whether it's operations or just the physical phenomena, if you can incorporate that, that helps ground your AI methods. So just as a trivial example, I mean, you can imagine a AI that does 0-dose CT. So you don't even scan the patient, but generative AI gives you a CT image, right? So you could say, here's my 0-dose AI. But if you incorporate physics, physics will tell you, no, you don't have an image because you have 0-dose. So, I mean, it's a trivial example, but there are definitely ways that you can incorporate physics into your AI and I think get the best of both worlds. So just a couple comments from my side. I think it just builds on everything that was already discussed.
All right. Thank you so much. So I guess, Tony, do you have any thoughts you want to say at this point? You're on mute.
Now me. Okay, I looking at these main and I mean I'm very impressed. If we could get images like that to analyze and they were top quality, that would be phenomenal. My concern is that the objective function here, and in most cases there have been some objective analyses, but in most cases It is that the image has a more pleasant appearance. And obviously that's a good thing. But the question I have is there any notion of how that may distort the geometry? And I'm meaning at the geometry on a small scale rather than the geometry on a large scale. If we're saying, is the lung the same distance across, I've no doubt that we are accurate to a millimeter. But the question is, if we're now in the context of a very small lung lesion, and the smaller we can measure them, the sooner we can come up with a diagnosis. So now it comes to the question of, okay, I have 2 reconstructions, but if I take a measurement, is there any AI evidence or assist here that can highlight whether my measurement is precise to within, say, 1 millimeter, when the number of pixels I'm looking at is not an AI number of pixels, is maybe in 3 dimensions, 100 pixels of that order, and most of the surface of the lesion is partial voxels. That is kind of where we would like to be taking distance measurements. And AI has not been overpopular for doing quantitative measurements, that I'm aware in this sense. So can anyone address, if you will, the small positioning geometry errors, which to me might be coming more from the mechanical device itself and the reconstruction algorithm presets, and how that would be addressed by AI?
Andrew, you were going to say something.
Yeah. I don't have an answer. I just want to say that I totally share this concern from and by the way, Adam's comment on the physics-based and physics-based AI, definitely it's something that I think it's the way to go. Something to be that we are aware is that some of these networks are kind of operating in the null space of the CT scanner. So they're trying to get you information that it's not directly in the acquisition, that the CT scan, for example, super resolution, if you have pixels certain size and certain parameters, the information you have is sampled at that size. If you want to get it smaller, now that is kind of missing information, and that's what traditional algorithms had problems. With AI, what you can do, you have a training that gives the kind of a priori information of how most people look like at that level, and that's what it's using to try to get the extra information. But it's important to know that these networks are almost everything I see in the literature are trained with like healthy anatomy, healthy patients. So they are not trained with thousands of lung nodules to find out the surface of the lung nodules. It's trained more on like hundreds of healthy patient lungs, and most of the pixels in the image are healthy anyway. And then it learns what the lung looks like. So it could make a super resolution of a lung, how the lung could look like. But if you're looking at the disease, and each patient has a very absolutely different disease, right? It's random anatomy. So I share the concern, and there is not very clear metrics unless you have perfect ground truth, like 3D printed images or synthetic images. That it's actually also what I use. It's very hard to tell that denoising or super resolution it's a fair representation of the anatomy. Even though it looks great to a human, it may not be exactly the boundary that patient has, because the network has to somehow come up with this missing information, and it may very well not generate it right. So I think it's the key of the next stage for these kind of things, to evaluate how accurate it is to truth, not just how nice it looks like.
Yeah, I would just
go ahead.
I would just add that so AI, we all know AI is very powerful, can create beautiful images. There's also a risk that it might create something that's not real, hallucinations. So I think we can prevent that by first making sure our training data set represents those cases. So of the results should not be standard IQ metrics like noise resolution, very task-based evaluations like the specific examples that you mentioned. Those can be we just need a comprehensive way of evaluating all those specific cases that nothing is imagined, but everything is as close as possible to reality.
So the problem, Bruno, is that virtually all of the phantoms and the nodules that are used for validating are at a higher scale, a centimeter or bigger. But we operate in the 3 to 10 millimeter range. So I think the big risk for AI, and even going back to iterative and model-based methods, is how do those methods, how are we going to make sure that those methods don't create additional features and structures or not capture certain structures down at the, again, 4, 5, 6 millimeter diameter size, for example. We can do that if we put effort and time into it. But I think in the past that has not been done. So we have an opportunity here as a group to start to form some working collaborations to at least get some data sets on the table for testing these things. I think this might. What do you guys think?
Yeah, like for example, you saw the virtual calcification example that I showed. That has a very fine structure that's completely not a sphere or anything like that, right? So you can imagine finding nodules with very random or non-regular architectures and using these in a virtual testing framework to ensure that those things don't happen.
Yeah, a good one of the better targets would be a small part solid lung nodule. Why do I say part solid? Because the non-solid part of a part solid lung nodule, first of all, it's varying. It goes from high density to low density, but then it allows the texture of the parenchyma to come through, right? That's the definition. So if we could produce some of those either mathematically or with 3D printing, and then see how well those textures and that ability to distinguish a part solid from a solid or something else, I think that might be a valid way of doing it. But anyway, again, what about the rest of the panel? You guys agree we need to do something here before we let the AI just go out into the field and we figure out what happened?
Yeah, absolutely. I mean, this comes back to my comment about we need realistic data where you have a ground truth, right? So I think that's what you're getting at, Rick. Something realistic to test not only train and develop the algorithms, but then independent data set to test the algorithms. I think, there's also this sort of dichotomy here, and even this session split up into, on the one part, there's the acquisition and reconstruction. And then on the other part, there's the image analysis once you have the images. That I think is still going to be important. I know there's some interest in sort of a complete end-to-end, direct prediction of that Bruno mentioned. That makes it even more of a black box, I feel, and then also would cut essentially the human out of the loop. At least for now, with the 2-stage, we still have the ability to look at the images and have a human expert in the loop. But it also gives us an opportunity to independently test the 2 parts and even not pit them, but use them to evaluate each other, right? So you have a new reconstruction algorithm. Can you use your automated analysis? And is it getting you the result that you expect? Is it repeatable? Is it reproducible? And then vice versa, the new reconstruction algorithm or sorry, with a new image analysis algorithm, right? With this the same images. So I think at least we can break it down a little bit into the different stages, and that helps address the overall problem. Yeah.
Before we go on, I just want to touch on one question which you guys have all been prepped with, which is this question of bias. So if we train on all, let's say, healthy individuals, then when we reconstruct with AI, deep learning AI, are we going to turn people who are not healthy into healthy? If we train with ethnic biases, are we going to make mistakes across ethnicity, age, gender? And the list is immense. I mean, the possible subgroups here is incredible. So again, how are we going to try and possibly get the diversity in the training of these AI methods? I'll throw it to you first, Bruno. What's your thought?
So yeah, my initial impression is that bias is much more prevalent in the image analysis stage. For reconstruction of images, I think that's perhaps less important. Like if you do a tomographic inversion, AI should not know if that's a female or a male, right? I mean, you could argue there's a little bit of prior information in the image generation, but at least I think that's a much more important factor in the image analytics than in the image generation. That's my initial impression.
But you agreed before that hallucination is a concern. So if you combine bias and hallucination, you could have some subgroups getting more hallucination, some less. That's where I was going.
I think of hallucination more as ideally any nonlinear reconstruction algorithm, and AI is an extreme example of that, tries to suppress unwanted things like noise and streaks and tries to preserve all the real anatomical information, right? So in my mind, hallucination is where that breaks down, where something is amplified that's not real, but there are already some indication in the images. So I think that's more related to an instability of some of the generative AI than some prior information that it has from certain subgroups of humans.
That's good to hear. So we should take a question. Tony, do you see one here that we can't take them all? We probably should take one right at this point.
I'm seeing.
Well, one interesting one I saw was question: should we have two reconstructions, one for the purpose of AI analysis and one for the purpose of showing to radiologists? So I don't know if anybody wants to comment on that.
We've been promoting that in the Kiba small lung nodule profile for a long time. So it's not a new idea for AI, but it's clearly the way to go, because humans can't keep up with the amount of data you can generate in a CT scanner. Does anybody disagree? And N is not always 2 either, by the way. There might be multiple diseases and multiple nodule environments that you need data on, but I'll cover that in the next talk.
But there's an issue here of identifying abnormality. I would suggest that, again, you're training. An abnormality is something that is hard to train on because it is different for every patient, for every case, for every image. And is there a way to train to detect something that is unusual from a healthy is that a generic thing one could train for the AI?
Again, are you talking about a classification type task, or are you talking about like a reconstruction type task?
I guess to a point, it seems like it is both now. If your reconstruction is based not on the image data, but on the collective knowledge of a group of like cases. Do you not now have some mechanism for, do you make that which is not normal, which I guess is the one concern, or can you be very sensitive to something that does not fit the generic model you've been trained to? So I find the issue here is that you're getting inputs that you've not trained with, and I don't quite know how to reconcile
So
that.
the thing in general with the products that we're talking about that exist today, in general, what we're trying to do is estimate the noise in the CT image. So like what image? And we're estimating the noise in the CT image. We're not estimating the anatomy in the CT image and then subtracting out the noise. We're estimating the noise in the CT image. So to the extent that the noise in the CT image is similar between different anatomies, that's why the networks work robustly across different anatomies.
Yeah. Oh, okay. So the issue is that if you go beyond noise, if you start to get into using prior information to help you reconstruct certain structures, not just reducing noise, we could get into some trouble. But we have to move on, unfortunately. We have one more panel, and we have a talk that I have to give now. So I want to thank the panelists. Please stay on, of course. We're gonna possibly intersect some of these issues as we get into the next topic. So let me hand it over to Tony. Tony, do you want me to introduce folks, or do you want to do that?
Your voice diminished there. I guess that I am to introduce you, which you have already done somewhat adequately, but I will just follow through with a few words here. One second.
So yeah, we have three panelists, and feel free to introduce them.
Okay. That catches me unfair. I thought I was going to introduce you for this one. You were going to introduce the panelists.
Let me get started. So we have some of you may have heard of this fellow, Dr. Oudkerk. Sorry. He apparently won an award from our esteemed colleague in the name of Jim Mulshine. And Oudkerk is, as you know, leading CT screening in Europe, and is at the University of Groningen and iDNA in the Netherlands. We also have Dr. Stephen Lamb, who's at University of British Columbia. He, I should say, Matthijs Oudkerk also advises many other countries around the world on how they should do screening. So then we have Dr. Stephen Lamb, who handles screening at University of British Columbia, and also advises several other countries around the world on screening. And then finally we have Artit Jirapatniko, who's at Mount Sinai and is one of the core technical people at Mount Sinai, developing algorithms and systems and other things around screening for many decades now. So what I'll do is I'll just jump into my presentation because I'm already behind. I'll share my screen. Let's see here. That's interesting. I can't see my bottom panel because of this. Hold on a second. There we go. Okay. So if you're like me, you've been watching the space telescopes do amazing things over the last 20 years or so. Basically, we went from this Spitzer telescope looking at this constellation of stars, and we got a big improvement recently in 2021 with the Webb telescope. And every day, I'm seeing more and more just stunning images, great improvements in resolution and noise and many other things that we just never had before. So it's just truly staggering. And last year, I just got into this question of, I know we got photon counting CT. These are very expensive machines, but for the general lung cancer screening site who are using older scanners, why aren't we seeing something similar? If you look at publications back from 2000, 2007, they're using 1.25 millimeter slice thickness and spacing. And in 2023, this is a publication, I just grabbed an image. It actually looks a little worse, but it's about the same, 1.25, 1 millimeter slice thickness, 1 millimeter spacing. So the thought was, one of the big issues we have is that we try and do a one-size-fits-all scan to detect lung nodules and measure them. So basically, I put together a 3D printed object. This is tiny. You can see the ballpoint pen here to the right. It's 3D printed with these cones, 8 millimeter long cones sticking out of it. Very hard to make, but we made them and we put them in canisters, and we scan them. And if you multiplanar reformat and you look at that scan, because now you're taking 512 by 512 pixels and you're stretching it across, let's say, a typical field of view, you're going to get a blurry image of that tiny little object. And that's what's happening all over the world currently today in lung cancer screening. And then we're going further, they're going to try to measure that and see if there's change in that, which is going to have a lot of error because those boundaries are partial volumed all over the place. So, but what if AI were to look at that image, search for any focal abnormalities that are very serious, and provide physics-based guidance to the technologist for when and how to obtain a much higher quality scan of that abnormality. And imagine we did that in seconds while the patient is still on the table. We actually can potentially do that today. If you were to do that, I'll just give you one example, and this is not optimized. If you took that exact same image, because we did it, and you doubled the Z resolution, so let's say you went from 1.25 to 0.625 millimeter slice thickness and spacing, slice thickness, and you used double the dose, we could have maybe gone for radical 2, 1.4 or 40% more dose, which would probably have been the right thing to do. Bruno will correct me later, I'm sure. And then if you considered Nyquist, and even above Nyquist sampling, because in real world settings, you have to, things aren't perfect. So if you did 4 times the sampling that you see here in X, Y, and Z, you'd have, let's say, 64 times more samples. And those samples are not empty of information. They actually have valid information and using the CT scanner to do the interpolation. So, so you can see here on the right, if we were to, for example, measure the distance of these spikes, or they were intended to be something like spiculations, but it kind of looks like a star in the end. So sorry about that. But anyway, bottom line is it's much more visible. And if as was mentioned in the earlier panel, you definitely want to take into account imaging physics and signal processing. So there's a fundamental trade-off between resolution and noise. I know that gets a little different with AI methods. And when we start introducing AI methods on the formation of the image, that's going to be an entire other discussion. But we do have some fundamental properties that we can at least try to respect when we give guidance to a technologist for what to do next with the patient. Do we do another reconstruction? Do we do another scan and reconstruction? And then when we say what the sampling rate should be around that nodule, we should be using fundamental known sampling theory equations for how to calculate these things. And I'm just giving 2 examples here. There's many, many more. So it turns out, of course, that we've been, as you know, as I presented earlier, we've been doing fundamental, basically CT calibration, getting resolution, noise, other things with phantoms. And we've got huge databases now from scanners all over the world. They're coming in, these scans are coming in every day. And we have a great starting point for being able to basically guide technologists on how to get the next scan if it's warranted. So there's an exciting possibility here that we could, in this case of just measuring the length of these objects emanating from this ellipsoid, we're seeing in this first experiment here a 600% improvement in both the bias and the precision of the measurement, which is you know, a big deal. That's not a small change. So we also I looked at the volumetric differences between each of these spikes. I tried to estimate them, and to be honest, there's quite a lot of effects going on here. At the base of these, they're getting fatter, but at the ends, they're disappearing. So in the end, they're kind of offsetting each other. But so different measurements, different shapes are going to have different improvements or different performance, unfortunately. And I think that's true for current CT scanning as well. We just haven't done those types of experiments. But the bottom line is what's on the left looks a lot worse than what's on the right, and very much different than what was manufactured. So another thing we did recently was we started to produce, it looks like a wine bottle. The reason why it looks like that, or a jug maybe, is because I wanted something that I could rotate using centripetal force to get the resin out of these voids that you see here in this object. So we created a 3D printed object with very precise internal air-filled voids, and you can see it right there. And when we segment this with ITK snap, it turns out that the volumes of these start to bleed into one another because the sampling just isn't high enough to distinguish the boundary between them. And as a result, we're starting to get 800% or 1,000% improvements. And you can see that the green ones have now joined right here, and so have the reds, and that's why the biases and the precisions go crazy. And this is on a Discovery CT 750. This is on a Somatome Definition AS. You can see some pretty substantial. If you were trying to measure these small structures, let's say a feature of a lung nodule or part of a structure or an airway or something else, having a targeted acquisition available to you immediately after scanning could have potential really big improvements, especially if you're doing radiomics and you're trying to measure textures and other things. Having this additional information could reveal features and biomarkers that we don't even know exist yet. I also want to point out that we tried to measure the spheres, 1.5 millimeter diameter spheres on the outer ring of this, and they weren't even measurable with the ITK, segmentable with the ITK snap. So in effect, they were not measurable before, and now they become measurable. So what do you say? That's infinitely better. It's much better. Let's just say that. And here it is with the Siemens Somatome definition. So we've tested this on multiple scanners with multiple geometries, with targeted acquisitions. If AI were to find an abnormality and come in and suggest a targeted acquisition, possibly with additional features turned on or off, like metal artifact reduction or motion correction or other things on a per nodule basis, there's the potential for really tailoring an acquisition to the nodule and the nodule microenvironment, which I don't think has ever been done to date. Now, you might say, well, that's interesting, but you're not showing me clinical data. So here's clinical data. And on the left is a coronal reformat that shows an area with a lung nodule on the top left and some airways and vessels on the bottom right. And you might notice two bifurcating airways down here on the bottom right. And if you try to find them in the left image, these are actually the best website I find to try and play this. I would not carry things like that's the best really can do with this kind of data. And again, remember, what's on the left is what's happening today all around the world with 1.25 millimeter slice thickness scanning, which is the state of the art of current capability around the world by radiologists. Here's another example. You'll see a bifurcating vessel, but notice there's smaller vessels even coming off of that. What's the significance of that for COPD, for airway diseases, for other things? We don't know because we've never had data like you see on the right. Okay, not in any large scale. So there they are, totally invisible on the left, able to be distinguished on the right. So very exciting possibility that if we were to employ this type of method in real time on CT scanners within seconds, we might be able to greatly improve our ability to not just visualize these structures, but also measure them because AI can then come in and operate on this much higher quality scans. So there is a limitation though. A lot of CT image and a lot of CT protocols have image quality issues. Like you see on the right, you see those are actually ellipsoids with cylinders passing through them. And you see the scalloping of those cylinders. That was not there. The printer did not do that. That was done by the reconstruction method. And the site was using a tin filter. They were using automated dose, automated dose delivery with a specific algorithm that could contribute to this. So the good news is that we have a lot of phantoms and software tools to understand these image quality issues and try to avoid them. The bad news is that this will take time scanning phantoms to figure out what the right protocols are for targeted acquisitions that can give us much higher performance data. So the potential implications are that CT visualization and measurement of small objects can very likely improve by many times our ability to visualize and measure small objects. This very likely applies to all CT scanners. We're not potentially asking people to go buy new scanners. This could be potentially added to current scanners. Also, I want to point out that if AI screws up, the worst thing it does is suggests another acquisition to the technologist, and we have a human in the loop able to say no. Okay. Also, if it misses it, we just go back to standard of care. If it misses the abnormality, we go back to standard of care. So there's not a lot of potential bad things that can happen, I think, here. But let's see what the panel says. Follow-up scans can potentially improve can be brought in much earlier, weeks versus months. And radiologist decisions on lung nodules can be made with higher confidence and accuracy because they're going to have much better data. Numerous other applications are possible here in vascular, PE, COPD, and even trauma. And clinical trials using imaging to assess drug efficacy may benefit from these methods. We haven't even looked at that area. Imaging research into AI for detection and radiomics will be improved. And we have only explored the initial potential of these types of methods. There are numerous other variations, and I really want to thank really 4 clinical sites for spearheading this. Jean Arsenault in Quebec, Stephen Lamb, who's with us, Mario Silva at University of Parma, and David Yankelevitz at Mount Sinai. So thank you very much. Tony, I'm turning it over to you to moderate and have others talk. I think you're
well,
on.
I guess, well, not now. But we start off with Matthijs and go through the panelists, see if they have comments on what you had to say. I mean, for me, from a technological viewpoint, if you want to see something more clearly, you just zoom in on it, and this is true certainly for CT as it is for any imaging device. But maybe I should hear from the panel first on this.
Shall I make some comments on what I heard so far? Can you hear me?
Yes.
Yeah, okay. We are doing in Europe a foreign implementation study to answer all those questions you raised now, and I think all the questions you raised now are very relevant. But we are implementing AI in a fashion that we do the first read by the radiologist, the second read independently by the AI, and if there are discrepancies, we do an expert read between the discrepancies. So with this, we include now. So we have an extremely standardized. So we go in an opposite direction as most AI developers. They believe in this black box. Put all the data in, and the truth will come out. And we have another approach. We focus on the tasks that AI can take over from the radiologist. So we focus on all the decision making that the radiologist is doing in stepwise. And then we analyze if the AI can take that step over. So where at the moment everyone is focusing on characterizing the nodule in a fashion that it could almost take over histology, we don't believe that that point will ever be reached because the limitations of the acquisition technology. We focus on the negative predictive power of imaging technologies. So instead of a rule-in principle, we use the rule-out principle. And the advantages of the rule-out principle is very relevant if you have relatively low prevalences in your population. So we know, for example, in the Dutch population that there is only a 1% lung cancer rate in our screening population. Perhaps we can improve it a little bit, that it will go up to 2%, but that's all. So it's an extreme important feature of an AI if it could indeed get 90% of all the images out, all the participants' examinations out, because they have no relevant abnormalities, and that would give a very high impact. We would leave with the 10% that is still should be worked up further, and that 10% can be used for further workup of imaging features, for further refining AI on the positive side, and then also make steps to which nodules and abnormalities you end up with, where you want to really become invasive and take action and get histology. So that is the decision-making algorithm that we use. Now, furthermore, what we are doing is also in the opposite direction. We go to extreme standardization. So we have the high-end CT systems, dual sources of the latest generation. And with this, we could develop one acquisition protocol, which is able also to image non-gated, reliable calcium scoring. And that is really not something that's very easy, because the calcium scoring in itself is extremely sensitive to any motion or any changes in the acquisition protocol or whatever. So we developed that together with Thomas Floor, and which is also, and that is important, that you do not have to repeat it, or that you have to do CT gated or triggered calcium scoring. And then we tested it, we published it also, that the calcium score can be reliable, be done with this dual source high-end latest generation system. So that's the 3rd generation. If you compare it with CT ECG gated acquisitions. So that is what we already published, and we also published the manual calcium scoring versus the AI calcium scoring. And this process can, if you do it with this kind of acquisition systems, and then you use the AI as we described in our publication in JACC Imaging, you can completely take over with AI the calcium scoring. And then you have some misses, which we are refining, but those misses are 2 out of 1,000. So very, and those are also high number studies, very well qualified. And we also tested it in the data of the Robinska study, which also the mortality results will be published soon. Now, that is one part. The other part is the nodule part. And with the nodule part, we are now testing in what we are running at the moment, so that really goes in thousands. We are testing 8 different segmentation algorithms for the nodules. And from this, we learn that it is now 2 things. First, that the acquisition is fairly reliable at the moment that the solidity is more prominent, and is getting unreliable if the solidity is getting less. And it's getting so unreliable, especially if you have nodules lower than 100 cubic millimeter, and we can come into that. What is the anatomical reason that this 100 cubic millimeter is something that is really a threshold for many other diseases also. There you run into difficulties if you go lower. That we said, okay, we should not focus anymore on this subsolid, non-solid, and solid discrimination, because that is focused on, that is using segmentation algorithms that no one is aware of, and we do not know if they are comparable. So the segmentation algorithms that are used in the industry are vendor dependent. So if we measure a solid nodule with vendor A, then it can be also completely different, the same nodule, with vendor B, C, or D. Now, the problem in phantom studies is that this subsolid and non-solid and the solid component analysis is very difficult to mimic in a phantom. So what you have in a phantom, we did many phantom studies. You work with, I would say pure solid nodules, and then it all works well. So we think the discrimination subsolid, non-solid is not valid anymore. So what we are doing is we test many nodules with 5, 6, 7 different segmentation algorithms, and we see that the segmentation algorithms give a more equal outcome at the moment that the solidity increases. But many of the nodules are, as I said before, not really solid, and the solidity is getting better at the moment that the nodules are larger. So the measurements are becoming very reliable also between vendors when the volume is going over the 200 cubic millimeters, 250 cubic millimeters. But if you are around 100 cubic millimeter, you really have to also validate pure from the very beginning if the acquisition from the different vendors gives you the same with this one acquisition algorithm that they provide for the analysis, if they give you the same outcome. So we do this testing. We transferred the diagnostic algorithms that we used in the Nelson study and implemented those algorithms in the first read of the radiologist now in the following study. So we get exactly the same analysis of the nodules as we did in the Nelson to, more or less safeguard that we could get the same results as in the Nelson. Furthermore, we do now in a comparison to improve this many more diagnostic segmentation algorithms. Now we learned also that the VDT, so if you compare, we have now hundreds of fully automated AI, fully automated comparisons of AI, and we learned also that, for example, there's a huge kernel dependency. So if you do the reconstruction in different kernel, you will get different outcomes, and not small different outcomes, really 10, 20, 30% different outcomes if you use another kernel. So we need kernel standardization. Furthermore, if you use iterative reconstruction, as is promoted here, you will get artificial calcifications in the nodules. If it then is AI analyzed, you will get automatically a benign nodule, which could, for the, with all knowledge we have so far, could be also non-benign and could have a certain lung cancer probability rate. So and then the emphysema, and you have to do a complete different. There, the noise is the extreme difficult problem. So we compare now thresholding compared to cluster analysis, and we learned also that you have noise clustering. So there is something like noise clustering that goes up to 3-4 millimeters, and that is really influencing your measurement of the emphysema to a very high extent. And also the thresholding, so of the Hounsfield units at -950, which is traditional already there from the 80s of last century. Also, this threshold can be optimized, and we are doing studies on this, and we think that it should be a little bit different to get better and less inter-observer results, and also a better concordance with the AI itself. So that as a kind of initial comments on what we heard so far.
Thank you so much, Matthijs. And there's a very complicated overall assessment here. So maybe I can move on to Stephen. You have some comments on this?
I just have a couple of slides to show. So while the slides are being pulled out, I just want to thank Rick and Tony and the Prevent Cancer Foundation for asking me to take part in this panel discussion. And next slide, please. So as we have heard, we have lots of innovative work in next slide, please. Quantitative work and AI in lung cancer screening. So we just want to make a few remarks as to how we can capture the opportunity to advance some of these innovations into clinical practice. So I just want to give one example. And this is from the study from the Early Lung Imaging Consortium, or ELIC Consortium, a paper that we recently published, that Rick and others have published. So I just want to use an example of a lung nodule volume. So as we have known for quite some time, volumetric measurement is more sensitive than 2D measurement. So it's illustrated by this study. Look at the benign lung nodule, even it's less than 300 cubic millimeter. If you compare two scans taken several months or year apart, the mean volume change is very small, in the order of about 6%, with a very tight coefficient of variation. So if we do volumetric analysis in high quality CT scan, as is shown on the right-hand side, compared to 2D measurement, we can demonstrate the improvement in sensitivity and specificity. On the other hand, we use suboptimal CT acquisition parameter. We cannot show a difference. Next slide. So my question is, why is quantitative imaging of small lung nodules not widely used in clinical practice? If you look at how radiologists or the clinicians are still using, by and large, we do not do volumetric measurements in North America. So some of the reason is the CT departments generally don't have a QA system to assess the performance of some of this software. to look at the reproducibility and quality of the volumetric measurement. But this can be overcome. You just talk to Rick and we can find a solution. But I think a more important issue is there's no published data to show volumetric measurement resulting in a clinical benefit, like a stage shift, or provide survival or mortality benefit over a 2D diameter measurement. Next slide. Next slide, please. So this is my last slide. I just want to say that the opportunity is to do proper prospective randomized trial to prove that some of this AI approach actually improves clinical outcome. So in this example, I put down T1 as the nodule is first detectable on the CT scan. And then T2, if we use a 2D management protocol or standard of care in North America, we'll find the nodule that grow significantly to have a diagnostic workup. And then T3, we miss the boat and the patient come back with a clinical symptom and found to have a more advanced stage cancer. Now, if we do a retrospective study, if the AI algorithms say that you should have done the scan earlier, before T2, we could not actually demonstrate this benefit because we've never done a CT scan at this time point. On the other hand, if the AI algorithms say, well, the next scan should be 2 years or 3 years from the first one, if the patient come in with a clinically diagnosed lung cancer, then we say, well, AI is no good. So it's biased against AI if you do a retrospective study. On the other hand, if you do a prospective study using an AI algorithm, a single arm study, we cannot show the benefit of AI either because it's nothing to compare. So this is the reason why I propose we need to do a proper randomized trial to compare AI algorithm to manage lung nodules versus a conventional 2D measurement. So just to summarize, I think we need to use what we have and show that it is useful while we're working on some greater and better things in analysis of the CT scan. So I think I'll stop here.
Thanks very much, Stephen. I think in the course of time here, we should hear from Artit as a third member, and then we can come back to more our questions on the whole group here. So, Artit, you have a response, or?
Yeah, thank you to you, Tony, and Rick for inviting me to be on this panel, and the Brain Cancer Foundation. I think my co-panelists did a great job of kind of summarizing a lot of the issues in terms of the quantitative measurement. So I just make my comments concise. What Rick was discussing in terms of the AI targeting, I would just say that it's very logical. As you were saying, Tony, if you want to get a better image or a better resolution image of an abnormality, zooming in and giving it more dose will get you better quality. And I have to say there's precedent for this too as well. Back in the early days of screening, when you had your single slice and 4 slice scanners that would only do 10 millimeter slice thickness for the whole lung, it was very common back then to take targeted scans of just the region around the nodules at 1 millimeter slice thicknesses. So this is sort of an AI driven version of that. And I'd also like to say that, in addition to the work that you were presenting, Rick, on how it helps with the measurement, I'd also like to highlight that this would also help in terms of other AI and deep learning themes in terms of like radiomics, if you're trying to extract features and do classification. But I think this also raises another question of how low do we need to go on dose and what the trade-off is with image quality? Because I feel like with all these new these new reconstruction algorithms, both the iterative and the AI based, it seems like rather than using it to improve image quality, they're keeping image quality at the same kind of, let's say not as good as it could be, and then just using it to lower dose. And how do we, you know, where is that threshold? Because I feel like if you were to look at a diagnostic scan at this point in time, you can say that, you know, the image quality is much better. And as a person working in AI and quantitation, you know, I would love to have these kind of high dose, high resolution scans for everything. It would make my job a lot easier. But you know, I understand that there is this trade-off that that we're making. So those are my thoughts. I guess we can discuss some more.
Okay, Rick, do you have any response to that, or should we just open up to general discussion at this point?
I generally agree with what Artit had said. Yeah, let's dig into some additional questions.
Yeah, I'm not seeing any specific questions. So, Stephen, if I can ask you a question on your proposal for a study here. Is your hypothesis that an earlier measurement with volumetric would provide an equivalent performance to a later one with a 2D measured, or is it a simple trade-off between a 2D and a 3D to say which is providing the best kind of outcomes?
So what I'm saying is supposed to use for the metric measurement, which Matthijs and others have shown. You can do very accurate measurement to look at nodule growth. So obviously you have the potential advantage of moving the diagnosis to an earlier time point compared to 2D measurement. But we have never demonstrated into a head-to-head comparison. So this is very reason why very important to have such evidence for radiologists and clinicians to embrace this kind of technology, right? So which is not there. But this is separate from technological advances that, as we have seen, right? So but from a clinical point of view, we have to show that one management method like lung rats is same, inferior or superior than volumetric measurement. This kind of data is not available.
So are you suggesting that the current standard of 3 months is too long a period, that we should be exploring something like a 1.5 month period?
So I'm just going back to one of the earlier presentation by Dr. Sequist, right? I suppose you look at a second, even though it's so-called normal, but you say, well, this guy is going to have a tumor within a few months, that you should have done a CT scan in a few months' time, right? But you haven't done one. How do you prove that that concept is correct? So that's why you need to have a comparative study to show the advantage of some of this technology before one can say this is useful. We should change our guidelines to embrace that, right?
Need to do the study, yeah. Do we have any questions from the?
Could I comment on this?
Certainly.
Yeah. No, yeah, we did an analysis on everything that has been published on the VDT. And from all the publications that are there, you can indeed find quite a lot of information in different studies on the volume doubling time for different histological types. And from this is very clear that with the measurements of the VDT as done by CT, there is a definite separation between the small cell lung cancers, the neuroendocrine lung cancers, and the adenocarcinomas. And from this literature analysis, we learned that almost 70% of the adenocarcinomas have a slow growth. And what we also find out that the key differences between the NLST and the Nelson is that we have an extremely high percentage of small cell lung cancers early detected. And that is probably also one of the major reasons that we have a far better mortality reduction in males. Now, this altogether is done with volumetrics, and we published many papers on the implementation of the VDT and of the volumetrics, and also in the comparison with diameter, we did several papers, but that is indeed in European journals. Dus we are happy to provide some of those papers to those who are interested in this. And we did also an overview in the Lancet on the differences between diameter and volume measurements. But I think the penetration of our European journals in the US is less than the US papers in Europe. So that explains perhaps that some things are a little bit out of your perception. But I think if you look to all the developments worldwide, I think that volumetrics is widely accepted at the moment. And I'm a little bit amazed that this discussion is still there in the US and in Canada. So that is my response to what Stephen brings up.
May I make one comment? I think I pointed out the pitfall of a retrospective analysis, because we did not do a diagnostic imaging study or other workup at an earlier time point that's supposed to be advantageous for the patient. So we cannot actually prove the point that way. But you look at us in Canada, our program, our screening program, is the only one that uses volumetric analysis. None of the radiologists in other provinces, they all use the lung RADS 2D measurement for management. So I just give you, I'm similar in the US, where how many centers actually use volumetric measurement and get rid of a lung RADS guideline? With very few, right? So I think we have to address this issue by providing solid evidence. I think it is so.
Yeah, it's a good point. So, and if I could come back, Matthijs, given the higher ratio of small cell, would you suggest that an earlier time for a second scan would be appropriate then? Or given a volumetric analysis might identify even earlier than the current protocol?
I think that it should be analyzed if there is anything valuable in the civil AI analysis. It's probably based on the volume of the nodules. So that is something that is probably not understood. But I think that will be the key relationship between the lung cancer probability rate and what AI is detecting there. Now, furthermore, I think from different perspectives, it's quite clear if you want to measure the VDT in a reliable fashion, if you want to do it in a 1.5 month, you will only catch the very fast growing ones, because otherwise you have no difference between the two scans. So 3 months is, I think, the minimum you need to get a volume doubling time that is beyond, so lower than 400 VDT days. And also from just calculation base, you would end up, if you want to have the fast growing, so that I think the upper margin of those that are malignant is around 400 days. So if you want to catch them all in a reliable fashion with the standard deviations that are there, if you want to catch all those, you really need 3 months. So shorter is, I think, no option. You could argue longer, as Lunga says that you could even go to 6 months. I think that's too long, but you need some time. You need some time. So if you do it after a week, there's no way that your instruments are precise enough to really find a reliable VDT.
I have a comment here from Jim Mulshine that the next lung RAD upgrade includes volumetrics. So,
oh yeah, okay. I have my answers. That's nice.
I have a question here from David Yankelevitz, is there now a size threshold where the group agrees that volumetrics is too unreliable for use in clinical care?
Well, that's not my statement, by the way. Okay.
Any other comments on that?
All the recommendations, so PTS, EOPS, LearnRats, everyone is now settling down around the 102 millimeter, which is 5.8 millimeter, but okay, they rounded up to 6 millimeter. And yeah, the approach that David, but he's not there anymore. But he had an approach of the two measurements, so the longest and the short diameter, and then come to a kind of rounding up of the volume, is a better approach than diameter alone, without any doubt.
And then there's the thought that that Rick brought up is if we were to do a targeted scan through AI, maybe with that much more detailed image, we could get both a smaller size and possibly or shorter time interval. Does that seem reasonable?
No.
Or would that be good?
No. The problem here is from a technical point, yes, but then you run into what I call the homo pulsans. So the whole vasculature is pulsating. So it will have all over in the lung, not only the respiratory movements, not only the diaphragm that moves, but also in the upper lobes, you will have the problem of the pulsating of the arteries over there. So this all gives you at least an inaccuracy of 1 millimeter.
So I would agree with you, but the clinical data we've acquired to date shows a benefit. So I guess we'll have to see what the data says overall.
And maybe there will be some positional difference, as you suggest, with motion and.
But there's a location issue, of course. So if it's very close to the heart itself, you probably in the transversal plane, the right coronary artery displaces over 5 centimeters in a second. So,
but you can make your protocol sensitive to location as well. So I think that if we're doing a targeted approach, yeah.
Actually, you could even go further and say, look for cardiac motion and compensate for it if you see it, which would require more effort. But
now that was a very interesting question also from Stephen, where he asked how do you figure out where you are in the systolic or in the diastolic phase? And I think that was a very relevant question. And that can only be answered, and that was also the answer of Nagavi, that he said we exactly know by the ECG where we are at 70% of the diastolic cycle. That is true if you do ECG gating. But ECG gating or better triggering is not what you can do in a screening session. Just to get we did it in the Robinska study, and it takes you 10 minutes. It takes you 10 minutes to get a reliable ECG, and you have many disturbances. You have to do it again and over again. So for a screening setting anyway, in the way we do it in the Netherlands and in Europe, it is so much also cost inefficient. It will there's no way that you can reliably implement it. So if you do it, and therefore the question of Stephen was, I think, very relevant. At the moment you do not have the ECG information, then what are you measuring? And that is in fact the question of Stephen. And I think that's a very relevant question. If you are talking about the left ventricular volume and the right or any the atria of the ventricles, it doesn't make any difference. It is a little bit different for the muscle mass. So the muscle mass itself could be interesting.
Okay.
Because the
Well, I
muscle
guess
as itself, it gets an other configuration, but as a volume, it's going only to differ a very low percentage.
Definitely something to consider if you're going for a targeted acquisition. Is maybe you will know the location, obviously. So that can be something you could factor into the protocol. Okay, I think we're any closing comments? I think we're coming to the close to the time now, or is that not correct, Rick?
Yeah, we're all set. I think at this point we should hand it over back to Jim, who can tell us where we're going and what we're doing next.
Could I make
Okay.
one compliment to Rick? So I think what Rick is doing for the standardization of the phantoms is absolutely mandatory. So I do not want to give the impression that you just don't need it. It's absolutely mandatory. And even if you have this highly standardized way of working as Rick is promoting and is absolutely necessary, even then you have all those issues. But if you don't do it, so, and therefore also what is in the beginning, I thought that this challenge, and Rick can better, he has all the data, but that is also an issue. If you want to address all those comorbidities, then you cannot just go put a CT scanner in a mobile unit and just go around to get reliable data. That is, no, yeah, Rick has the data. He can tell us more about it.
No, thank you, Matthijs. It turns out that the worst data we've seen with our phantoms around the world has been in mobile scanners. So we have to be very careful with those, for sure.
Okay. Thank you very much. Very provocative sessions, and really highlights the complexity of what we're up against. And fortunately, we have some nice ideas for ways forward. We, at this point, are running a whole 3 minutes ahead of schedule. So that means that you're quicker to get to your break. But before you do that, I want to explain the process. The balance of the workshop today will be the breakout and the breakout sessions. And this year we will have 2 breakout sessions. Very simply, one's a clinical breakout session, and that will be conducted in this room. And so for people who want to participate in the clinical breakout discussion, it will be led by Al Rizzo and myself, and with help from Rowena Yip, and we stay tight. The second group is the technical group that will follow up on the discussion that we've just been having in the last session. And that will mean that after the break, those that want to go to the technical yes, those that want to go to the technical session, there's a link demonstrated in your chat where you could just click on that, and it will take you into the technical session where you'll spend from 4:30 to 5:30 reviewing the material that we just discussed, as well as considering new proposals. And so I would encourage you to, in the technical group, come back, link in at 4:30 when we start the breakouts. And for those that are interested in the clinical stuff, just come back to this Zoom environment that you're already in, and we'll proceed from there. Any other concerns? If not, thank you so much. Thanks to the faculty for providing us with some very, very useful insights. Have a good break. Good, sir.